Example 3 says evaluate the integral of x to the negative 1/2 power dx. So here we want to go ahead and use the power rule that we just learned. So the integral of x to the negative 1/2 power dx is equal to, we want to increase the power by 1, so negative 1/2 plus 1, which is equal to positive 1/2, and then we want to divide by positive 1/2 plus c. So that's going to equal x to the 1/2 power over 1/2 plus c, and whenever you divide by a fraction, that is the same as multiplying by its reciprocal. So that's going to be 2x to the 1/2 plus c, and we can rewrite using square root symbol. So our final answer for this indefinite integral is 2 times the square root of x plus c. For example 4, we want to find the indefinite integral of the 4th root of x dx and the indefinite integral of 1 over x cubed dx. So let's do part A first. We have the integral of, I'm going to rewrite this as x to the 1/4 power so that we can use the power rule. And that is going to equal x 1/4 plus 1 is 5/4. And then we also want to divide by 5/4 and make sure we get that constant of integration in there. And then that is equal to 4/5 x to the 5/4 plus c. Again, I will leave it up to you to take the derivative of that and make sure that your answer checks out. For part B, I'm going to rewrite this as x to some power, which is going to be negative 3 in this scenario. So if we increase the power by 1 and then divide by that new power, we would get x to the negative 2 divided by negative 2 plus c. And that is our answer for that one. Here we can see a table of some integration formulas, and just want to highlight, so if you're taking the integral of 1, then that just results in x plus c. If you are taking an integral of some constant multiplied by a function, you can actually pull the constant out in front of the integral and multiply it by that integral like that. And then if you are integrating a sum or a difference, you can separate that into the sum of the integrals or the difference of the integrals, which is some really nice properties that we have here. So example 5 says evaluate the integral of negative 2 dx. So the integral of negative 2 dx, we can actually rewrite that as negative 2 times the integral of 1 dx. We basically pulled out the constant, and we know from the table above that the integral of 1 dx is equal to x plus c. And so we get negative 2x if I distribute that in. And if I multiply negative 2 times some constant, it's still going to be some constant. So I can still put plus c like that. And that is our integral for part A. For part B, we have the integral of 40 times x to the 9th power dx, and I can pull out the 40. So I just have x to the 9th power dx like that. We're integrating that. And then that's going to be 40 times x to the 10th power over 10 plus c. And that's just going to equal 4x to the 10th plus c like that. And for part C, we can use the third property in the integral table to separate this into the integral of x cubed dx minus, and I'm going to pull out the 9, x dx like that. So then that's going to equal x to the 4th over 4. And I could put plus c right now, and then what's going to happen is I'll have minus 9 x squared over 2 and then plus c again. And these are two different constants, but if I add them together, it's just going to result in a new constant. So usually we don't write two different c's and we combine it all into one constant. So we'd have x to the fourth over 4 minus 9x squared over 2 plus c. Example 6 says evaluate the integral of x squared plus 1 squared dx. Now, in order to use the properties that we saw in the above table, we actually have to expand this thing that's inside the parentheses. So x squared plus 1 squared is equal to, actually let me write it like this so it's easier to FOIL. So if we FOIL that, we get x to the fourth plus x squared plus 1. So that's x to the fourth plus 2x squared plus 1. So that integral is equal to the integral of x to the fourth plus 2x squared plus 1 dx. And then if we use the properties from the table, we'll get the integral of x to the fourth dx plus 2 times the integral of x squared dx plus the integral of 1 dx. And this will equal x to the fifth over 5. I'm going to save the constant for the end. So I could put them for each individual integral, but I'll just save it to the end. Plus 2x cubed over 3 plus x, and then plus our constant of integration. So this is our integral for example 6. Example 7 says, Mr. Kwan finds that the marginal revenue in dollars per unit from selling his boba is given by the function MR equals negative 0.006x plus 36, where x represents the number of units sold. Find the total revenue from the sale of 75 units. So if we want to find the revenue function, that's going to equal the integral of the marginal revenue function. So that's going to be equal to negative 0.006x plus 36 dx. And then I can separate that using some of those integral properties. So the first thing I did was I brought the negative 1 outside of the integral sign. And now I'm going to separate this into two different integrals and then also bring out the 36. So if I do that, then we get negative 0.006x squared over 2 plus 36x plus our constant of integration. So overall, our revenue function is equal to negative 0.003 x squared plus 36x plus some constant. Now, if you refer to your textbook writes this constant as plus k so that you don't get confused with the cost function. So I'm okay with either. You can put plus c or plus k. Either one is going to represent some constant. But again, your textbook writes it as plus k as to not confuse you with the cost function. Now, we want to find the total revenue from the sale of 75 units. And normally what we'd do is we would just evaluate R of 75. However, as we have it, because we have the constant of integration, we're not going to be able to get a numeric value yet. So what we need to be able to do is we have to figure out what this constant of integration is. And we need to rely on the fact that if you did not sell any units of boba, then your revenue is going to be $0 because you're not selling anything. So we're relying on the fact that R of 0 is equal to 0. And that's going to help us figure out K. So what I'm going to do is I'm going to plug in 0 for X in our revenue function. And we know that that is equal to 0. So this here, that becomes 0. This here, that becomes 0. And we have plus k, and we have that that's equal to 0. So we end up getting that k equals 0. So now we have the overall revenue function, which is equal to negative 0.003x squared plus 36x. And now we can evaluate r of 75. So if we do that, we get negative 0.003 times 75 squared plus 36 times 75. And that's going to equal $2,683.13. So this represents revenue from sale of 75 units of boba. Example 8 says, with U.S. Department of Commerce data for selected years from 1960 and projected to 2018, the rate of change of U.S. total personal income can be modeled by DIDT equals 12.59T minus 51.74 billions of current dollars per year, where T equals 0 represents 1960. Part A says, if U.S. total personal income was 8,429.7 billion in 2000, find the function that models I of t. So we have the derivative here, and in order to find I of t, that is going to equal the integral of di dt. And so that's going to equal the integral of 12.59 t minus 51.74 dt. And then that's going to equal 12.59 t squared over 2 minus 51.74 t plus c. So we have I of t is equal to that. Or let me write this up here. This is I of t. Okay, now, again, kind of like the last example, we need to figure out what our constant of integration is, and we need to rely on the fact that in the year 2000, there was $8,429.7 billion. And what that tells us is 2000 is 40 years after 1960. So I of 40 is equal to 8,429.7. And that's going to help us figure out our constant of integration. So I of 40 is equal to 12.59 times 40 squared over 2 minus 51.74 times 40 plus c, and all of that is going to equal 8429.7. So this thing here, that simplifies to 8,002.4 plus c equals 8,429.7. And then if you subtract 8,002.4 from both sides, you end up getting that c is equal to 427.3. So our final answer for part A, that's asking for the income function, is I of t equals 12.59 t squared over 2 minus 51.74 t plus 427.3. That is our answer for part A. And then for part B, it asks, what does I of t predict for the US total personal income in 2015? Now, 2015 minus 1960 is 55 years. So we want to evaluate I of 55, which is going to equal 12.59 over 2 times 55 squared minus 51.74 times 55 plus 427.3. And if you throw that into your calculator, we get that that's equal to $16,623.98, but this is in billions of dollars. And that represents the total US personal income in the year 2015.